The videos on network are there for you to be able to capture. Okay, so a network, when you hear the word a network, it's like something is connecting something. Okay. So a network is an arrangement where you are connecting nodes using apps. Let me draw that for you. You are connecting nodes using apps. So this is a node. Okay, I'm going to draw something here. This, why is the thing up? Oh. Let me just close this again. My writing is not happening. I don't know why it's not happening, but let me see if I can use this one. It's not really happening at all. Okay. Strangely enough, this thing is not. So, I hope you can hear me.
Yes, please, we can.
Okay. So a node and an arc. A node and an arc, there is a difference. Just a second. Okay, so what I've drawn here, this is a node. Okay, this is a node. A node is like a junction. This is another node. The nodes are represented by circles. Okay, but the nodes are connected. Now, what can represent the node? The node is like a junction. A junction. Now, if you look at Okponglo Junction and you look at Accra Mall Junction or Spanner Junction, those junctions are nodes and they are connected by arcs. Now, the arrow will show where the arc is going. So if you are from Accra Mall Junction, A for Accra, going to Okponglo Junction for O, that connection is an arc. And this happens on road systems. So you'll be hearing a lot about transportation. But it's not only on road systems, it can even happen in terminals. So in an airport, there are terminals, and each terminal is a node. And then you can have road systems connecting those terminals. And again, it's not only terminals or road systems. There are several examples. And these are some of the examples. Okay? Like, let me see what I can show you examples. Like switching points. When you are dealing with a switch point, like in your house, there's a switching point in the living room. There's a switching point in the kitchen. There's a switching point in the corridor. There's a switching point in the bedroom. These are switching points, and they are connected with wires. They are connected with wires. So the switching points are nodes. That's what called nodes. You can look at another example like pipes. The pipes are connected by pumping stations. So you have this pump, you have that pump, you have another pump, and they are connected with pipes. And inside the pipes are fluids. fluids passing through those pipes. And then you can have several other examples. So network model helps you to be able to understand the working relationship between nodes through arcs. Now, another name for the node, okay, is circle. And another name for the arc is branches. So you have circles, and these circles are connected through branches. The circles are connected through branches. I hope you understand this. Now, let's define, there are 3 types of these circles. And I'll talk about 2 for now. So the network model, you can apply it in several ways. So the network, first of all, know that the network is an arrangement of nodes connected together through arcs. They are nodes, junctions, connected together through arcs, like intersections, connected together through roads, airports, connected together through air lanes, switching points, connected together through wires, pump stations, connected together through pipes, okay, and several other examples. Okay, so we use this whole network model to understand transportation models, transshipment models, and assignment models. There is also the shortest path, the maximum flow, the generalized network, the minimum spanning, and the project scheduling. I will not teach you any of these ones, okay, because of your mental equilibrium status. So I'll be talking about only the first 3, transportation, transshipment, and then assignment. Now, but before we do that, you want to understand some few things about the nodes and then the arcs. Okay. I hope that this time this thing will work. So let me see whether it will work. So I'm going to show you something, and I want you to please pay attention to this. Wow. Now I've started drawing this, not coming again. No, it's not. I don't know why. I don't know. It was coming before. Oh. The thing is even going to. All right. So we have arcs and we have nodes. There are some nodes that yes, so I have these nodes here. You have node 1, node 2, node 3, node 4. All right. Now, there is a connection between these nodes, and I'm going to draw this connection using the arcs. Okay. There's a connection between these nodes, and I'm going to draw this connection using the arcs. So here is the first connection. You have from node 1 going to node 3. You have from node 1 going to node 4. I'm going to use a different color to indicate the next one. You have from node 2 going to 3. And you have from node 2 going to 4. Now, you can see that the arc is coming from one of the nodes and going to another node. The nodes that the arc is coming from is known as the supply node. The supply node. So normally we call that the source node, the source node. And then where the item is being sent to is known as the demand node. The demand node, which is the destination. So you have from supply node going to the demand node and are connected using the arcs. Each of the nodes have meanings. Each of the arcs also have meanings. So you can have a supply node that is supplying an item. So you can have a warehouse in Tema. And this warehouse in Tema is supposed to transfer some goods from the warehouse in Tema to another warehouse in Kumasi. And so the warehouse in Tema becomes a supply node, and the shop in Kumasi becomes the demand node. But the items that are transported are represented by the axe here. So your decision variable, what is your decision variable? The decision variable is what you got to decide on to produce or to send or to reduce. Your decision variable is the quantity of the items you want to send. Your decision variable is the amount of goods you want to produce. And so if you are sending some items from supply to demand, then the arc here will represent the decision variables. So note this down, that the arcs represent the decision variables. The arcs represent the decision variables. Now, normally we represent a decision variable with x1, x2, x3. Okay, normally that's how we do it. We have x1, we have x2, we have x3. Okay. But when you look at the thing, it's not only x1 that is here for this one. You can see that the item is from x1 going to x2, going to x3. It's from x1 going to x3. And so the decision variable cannot be just x1. Who can tell me what the decision variable will have to be? It can't be just x1. So what will it be? Suppose you take an item that you are transporting from supply node 1 to demand node 3. What will be the decision variable? Nagi. X13. So, ladies and gentlemen, this arc is represented by X13. And that becomes the decision variable. That is what we want to find out. We want to find out that from supply node 1 to demand node 3, how many of the items were transferred, were sent, were transported. And that is what we have here. If at this stage you don't understand, this is where you raise your hand. Okay. If at this stage you don't get it, this is where you raise. So we have been able to get. So who can tell me what to be the, so note, I told you that the acts are the decision variables. And by the way, the nodes, let me just write it down somewhere. The nodes are the constraints. The nodes are the constraints. So in this simple example that I've given you, how many decision variables do we have here? And how many constraints do we have here? Perpetua.
We have 4.
4 what?
4 constraints and 4 decision variables.
Okay, so what would be the decision variable if I were to transport something from supply node 2 to demand node 4? What would be the decision variable? From supply node to Rebecca, from supply node 2 to demand node 4.
That's X2, 4.
And which arc is going to represent that?
Arc.
Which arc? The arc have got colors.
The purple color.
The one on top or the one below?
The one below.
Yes. So the decision variable is going to be X24 for this one. And the decision variable for supply node 1 to 4 is going to be X14. Watch the way I'm naming them. It's very important. Now, please note that this is the simplest one you will ever get. In real situation, these nodes are many and the acts are also many. And the decision variable for the supply 2 to demand 3 is going to be x 2, 3. So now you know what the decision is. So the decision variables are actually x, I, j. These are the decision variables. They are usually x, I, j, where the I is referring to the supply node number, and the j is referring to the demand node number. Now, let's take a practical example and then come to appreciate it. Okay. Let's take a practical example and then appreciate it. So this is a typical example of a network. What do you see on your screen? Where the arrow is going is important. Where the arrow is going is important. Now you can see that in this example, there is a transshipment node added. We'll come to that. But for now, I want you to know that a transshipment node is simply an intermediary node. It does not supply nor demand. Okay, it supplies and demands at the same time, but does not have the item. A transshipment node. It supplies after it's demanded, and so the item is not in the transshipment node. It is from the supply node, it is going to the demand node, and the transshipment node helps that to happen. Let's take, for example, there is a car that is going from 37 to Medina. There is a car going to 37 and Medina. Okponglo becomes the transshipment node in this network. There is a car traveling from 37 to Medina. Okponglo Junction becomes the transshipment node in this context. So the car is full. All the people are from 37, and all of them are going to Medina. Nobody gets down in Okponglo. So Okponglo is just helping the route to be smooth. It's an intermediary node. It's a transshipment node. All right. So let's take a practical example and you will appreciate all of this. In a network model, the goal is either maximizing or you are minimizing. Please take note. What are some of the things you will maximize? Well, most of the time you're going to see that it's going to be much more minimized, but sometimes you maximize. Okay. Some of the things you will maximize, okay, will probably be revenue or profit. Some of the things you'll be minimizing will be losses. You'll be minimizing losses. You'll be minimizing distances. Please take note. You'll be minimizing costs. You'll be minimizing anything. For example, if you look at infections, COVID-19 infections, you'll be minimizing. So there are things that you'll be minimizing and there are things that you'll be maximizing. Therefore, when you are forming this, okay, so let me just give you something. This is very important before we move on. So suppose you have a decision variable, and decision variable is x1, 2. I'm sure by now you all understand the decision variable. It means that you have some items that you are transporting from node 1 to node 2. You don't know the amount of the item. That is why the amount is what? The amount of the item is actually the x1, 2. But in sending the items from node 1 to node 2, from the supply node 1 to demand node 2, you will incur a certain cost. Let's assume that the cost is $4. So you're incurring a cost of $4 for sending. But if you were sending the item from node 1 to node 3, that one, the cost you're going to incur will not be $4, but it will be $10. So each decision variable will have attached to it a certain cost, or if it is distance, a certain distance. And your goal will be to minimize the cost or minimize the distance. But you want to put all of the cost and the distance together and minimize all of them at the same time. And so you will have to multiply the 4 by the x12 and then the 10 by the x13, so that you will have something like 4x12 plus 10x13, and then do for all the others. This will be your z function, which you have to what? Minimize. So you will see that you are summing the decision variables, the x's, and also multiplying. So it's a sum product, multiplying each one by their respective distances or their respective cost, whichever one you are dealing with. And then you will now have a complete, model that you are going to minimize or maximize in this case. So when you look at this function here, this function is indicating what I just explained. So the C will be representing the cost multiplied by the decision variable. And that is your function. So we're going to take a typical example. And the typical example we're going to look at a transportation problem first. Okay. In order to look at a transportation problem, there are a few things I want you to note. In a transportation problem, the whole idea is that there is a source where some items are being sent from the source through an arc, through a certain road, through a street. Okay, some units are being transported and they are being sent from the source to a destination. There is a fixed number of items or units that are being sent in this case, but there's a cost associated with sending. Now, do you remember I told you that the nodes are the constraints? Okay, the nodes are the constraints. So let's take this, for example, this node. Okay, this is a node, and this is a supply node. This is another node. It's also a supply node. This is another node, a supply node. This is another node, a supply node. Okay. Now, suppose that the items that I am transporting, and of course, this is 1, 2, 3, and then 4. Please, you can have as many of them as possible. Okay. So normally the numbering should be for finish all of the supply nodes and then continue the other numbering with all of the demand nodes. So if you have something like this, and what we want to do is that, of course, each one will have an arc associated with it. Let's assume that the amount of items that you are supposed to supply from node 1 to node 3, from node 1, it is 100, but node 3 is expecting 140. From node 1, it is 200. But node 3 is also expecting some goods, but then the total number of goods that it is expecting is 160. Yeah. Now, remember that node 1 was sent to 3. There's no question about that. Node 1 will also send to that. Node 2 will send to 3, and node 2 will also send to 4. In this context, check the total number here. The total supply. What is the total supply? You can tell me the answer. And what is the total demand? Perpetual, what is the total supply?
300.
And the total demand?
300.
300. I deliberately made it like that. When the total supply equals the total demand, we have a balanced transportation model. And now listen. In that balanced transportation model, all the constraints are going to have equal to, because we have a balanced transportation model. What if we don't have a balanced transportation model? What if that the total amount being sent here, okay, the total amount being sent here is, say, 200. Then you know that the total demand is going to be 340. And of course, the total supply is going to be 300. So in this case, we have an unbalanced transportation model or problem. In this unbalanced transportation problem, because the total supply is less than the total demand, one of them is going to have the inequality. The other will not have the inequality. We'll come back to that and I will explain all of that to you. So I just wanted to know that there is a balanced transportation model when the total demand equals total supply. There is an unbalanced one when they are not equal. Okay. And that's what I've just explained there. So in a complex mathematical model, this is a general transportation model. It looks very complex, but it's not complex when you put the things in. Okay. So you are going to minimize this whole function, each cost multiplying the decision variable. And then you now write constraints. You have to write a constraint for the supply node, and then you have to write a constraint for the demand node. You're going to do that right here. And to do that, let's take this simple example. Please watch me and follow me here. Wheat is harvested in the Midwest. Wheat is stored in grain elevators in 3 cities. So they are harvested in the Midwest, but we are not told where in the Midwest they are harvested. But we are told that they are stored in 3 cities: Kansas City, Omaha, and DM. Now, the elevators where they are stored, these elevators will supply the items, okay, 3 floor mills. So they will send the thing to some mills. These floor mills are going to now work on the items. The floor mills are located in Chicago, St. Louis, and Cincinnati. So the grains are shipped to the mills using railroad cars. Each car is able to hold 1 ton of wheat. So the wheat is transported through the railroad cars. Each elevator will supply the following number of tons of wheat to the mills every month, of course, with associated costs. It's like sending oil from the depot to the hinterland. So look at the numbers here. We are going to use these numbers. So node 1, and I want you to be drawing this node. Node 1, you have the items from the Kansas City, and Kansas City is supposed to supply 150 tons of wheat. Okay. Now, this 150 tons of wheat, remember that Kansas City is supposed to supply all of that, not all of this, to each one of these 3. So this 150, it is possible that some are going to Chicago, some are going to Cincinnati, some are going to St. Louis. Omaha is also supplying 75 tons to Chicago, to Cincinnati, to St. Louis, to Cincinnati. DM is supplying to 275 tons and is going to Chicago, Cincinnati, St. Louis, and Cincinnati. So each one of them has an amount it is supposed to supply to. Can you draw the network model for me? Can you draw the network model? First of all, what would be the decision variables? Who can tell me? What would be the decision variable for this whole model. What would be the decision variable? Of course, what you are seeing here are the amounts that are, what do you call it? That it costs, the amount it costs to transport. So if you look at this number 6 is the amount it costs to transport from Kansas City to Chicago. The $8 is the amount it costs to transport from Kansas City to St. Louis. The 10 is the amount it costs to transport from Kansas City to Cincinnati. And then Omaha 2 has got a respective account and the rest as follows. Now, my question to you is, what would be the decision variable? How will you write the decision variable? The decision variable will have to be written as we know, X, I, J. But what do they represent? Who can give me a guess? Dorothy.
So please, let Xij be the amount of wheat to transport from elevator I to CTJ.
Amount of wheat to transport. Good. To transport from elevator I like that. Elevator I to mail.
Yeah, to mail J.
Mail J. Once you use elevator, you have to use mail. Otherwise, you say from node I to node J, if you don't want complexities, from node I to node J. That is a perfect answer. But after this, you have to define what I stands for. So the I are how many? 3. So you have to write that I is 1, 2, and 3. And what about the J? The J is how many? It's 3, but they were represented by A, B, and C. So the J is A, B, and C. You have to define these. You have to define the I and J. If you don't define this, your whole decision variable is not correct. So it's important to tell us what the I represents here, what the J represents. Now you can see that the J, I have used A, B, C. But remember that if you were to go by the simplest approach I told you, you can make J to be number 4, number 5, and then number 6, so that it follows numbers format. I'm sure you understand what I mean. Okay. Now that you've defined the decision variable, the next thing is to draw the network model. So who can tell me how many supply nodes are we going to draw? How many demand
3.
nodes are? Very good. What about the demand nodes?
Also 3.
Is it a balanced transportation or unbalanced?
It's a balanced transportation.
Okay. Ladies and gentlemen, I'm sure you can draw, can't you?
Yes.
Yes.
Yes. That word, yes, I like it. You know, it's one thing to say, yes, I can draw, and another thing to also draw. Okay, so let's see whether we can do a quick draw. So what we are going to do is I'm going to draw this. There are 3 supplies. Now, please note that it's not supposed to be beautiful. I just want you to know it's not supposed to be beautiful. So if it's not beautiful, don't worry. Okay. If it's not beautiful, don't worry. Don't worry at all. So I've drawn my 3 there. My first one, that's it. Demand nodes. So, for example, in an exam situation, I would suggest that she always use pencil. Makes it simple to deal with that than if you use something else and it doesn't show up. Now you have to draw the axe. And let me share something with you. When you are drawing the axe, you have to draw it in such a way that when you draw, you label it. Okay. When you draw, you label it. Let me just go back here and give you the numbers. 1, 2, 3. Please note that I'm using 1, 2, 3, 4, 5, but in the slides, I use, on this side, I use A, B, C, but don't worry. All right. And go check the the items, if you check the items from Kansas City, the total, let's give this name to be supply, and let's call this demand. From Kansas City, and the first one is Kansas City. The amount being supplied was 150, so you write it on the left. Then from Omaha, the amount being supplied was 175, so you must write on the left. Then 275, so you must write on the left. And that one is there from the DM. Then the demands. The first one was Chicago, then St. Louis, then Cincinnati. Chicago was demanding 200, so you write 200 there. St. Louis was demanding 100, so you write 100 here. And Cincinnati was demanding 300, so you write 300 there. Now, the arrow. Okay. The arrow is coming from node 1 going to node 4. So this is it. Once you write node 1 going to node 4, you write node 1 going to node 5. You show node 1 going to node 6. Once you've done that, quickly write the decision variables. The decision variables, attach it here. X14, attach it there. X15, why is it 15? Well, you look at where it is from and where it's going. And the last one is X16. Okay, that's what you do. Once you've indicated all of these, you also must add the cost. Remember, what are the costs? If you go to the slides, let me quickly take you there. You know the cost associated. From Kansas City to the other three, you have 6, 8, 10.
10, yes.
Okay. You have 6, 8, and 10. And so when you come to the drawing, you have to ensure that these 6, 8, and 10 the graph is not showing up for some strangest of reasons. Okay, so you write 6, 8, 10. Now those writings must be on the extreme end. This is what I want you to take note. They must be on the extreme end. And then you have to do for the node 2, going to 4, 5, 6. Then do for node 3, going to 4, 5, 6. I'm sure you get a point of what I'm trying to say. If you should do that all well, you are going to have something that looks like this. So you can see what I've shown you here. I am showing ABC in the demand, but don't worry. Okay. You can still use that. You can bring the cost first and then bring the decision variables at the edge, or bring the decision variables first and bring the cost at the edge, at the end of the demand node. But you have to finish one, name it, draw the arc, name it all before you go to the second one. If you don't do that and the arcs cross each other, and you are now going to look for which arc and name it, that is going to be quite difficult to do. So if you do that correctly, you're going to have this complete labeling. You see, even though you are seeing this complete labeling, it looks a little bit manya-manya, but it doesn't matter much because you now know where it's coming. Learning how to draw these nodes and the arcs and labeling it all will give you strong 7 points in an exam situation. Learn how to draw the arc, how to label it nicely. Any question on this? After you've drawn the arc and labeled it, the next thing is to answer these questions. Okay, so you can see the first one was to define the decision variable. The second is to develop the network graph model, showing all the cost and the decision variables, which we have done. Now we are going to write everything in a mathematical framework. How do you write the mathematical framework? Well, look at the table. You are going to take, in fact, when you have the drawing and properly labeled, you will be able to nicely finish this whole thing by looking at what you just drawn. So the first thing we have to do is to write the objective function. We know that this is a minimization because we were told that there are costs that are incurred for transporting. So your first thing you want to do is to bring your Z min. Yes, Hansen.
Sir, I have a question. Can you hear me?
Please go ahead.
Before that, I want you to display the question itself. There's something I'm confused with.
Okay. Yeah, this is it.
I mean the question itself, the beginning.
Okay, this is the beginning.
Okay, you actually have it here.